Welcome to the arithmetic zone and welcome back to integration by parts. So as I said in the last video, this time we're going to tackle on harder problems of the topic. In the last video, we covered 3 easy to medium problems. This time we're going to go a little further and we're going to see some new concepts that I haven't really covered in my first video. So as always, when you approach a problem that requires integration by parts, the first thing you should recall is the acronym LIATE, which I have to the right here. So what do we use with LIATE? We have to identify the 2 unrelated functions in our integrand. So I'm going to label u as x squared and du will be 2x dx. And that comes from here. Now for our second function in there, that'll be e to the power of x. Du is e to the power of x. And the antiderivative, okay, this should say dv. I apologize for that. V is just e to the x power because, you know, the derivative slash antiderivative of just e to the x power is just e to the x power. Very convenient. So now if you do not remember the formula for integration by parts, I got you. It's uv minus the integral of v du. With that in mind, what comes next after this, after our initial step, will be the expression x squared e to the power of times e to the power of x minus the integral of 2x times e to the power of x dx. So in our earlier videos, after we use that formula, what we would do is just do some simple integration methods and then we get our final answer. But this time it's not so simple, because when you look at our expression right here, specifically the integrand, you will realize that, you know, I can't use simple integration methods right here. I can't use u-substitution. I can't use modified u-substitution. I can't use any, you know, the special trigonometry, anti-differentiation methods. So what we're actually going to have to do is do integration by parts again, but we're going to have to do it for this integrand specifically. So u is going to be 2x, and then du is just 2 dx. And then for our second function is once again e to the x power. So we already know what that's going to be like. So when we do integration by parts again, and you know, we recognize all of these recognize the 2 unrelated functions, we're going to have to split this integrand up specifically into that formula again, uv minus the integral of v du. And what that turns out to be is x squared e to the power of x minus all of 2x times e to the power of x minus the integral of 2 times e to the power of x dx. This time, you can see on our integrand, we can just use simple integration methods because there's no other variable other than just e to the power of x. But first, let's rewrite this whole expression. So we distribute this negative sign right here. So x squared times e to the power of x minus 2x times e to the power of x plus the integral of 2ex dx. As I said earlier, the integral of just e to the power of x, when its coefficient is just a constant, is just e to the power of x, and then you keep that constant. So that's our last step. So what we get for our final answer is going to be x squared times e to the power of x minus 2x times e to the power of x plus 2e to the power of x plus. Remember to never forget the constant of integration when you're dealing with these indefinite integrals. Anyway, let's go on to our next example. Example 2, we have tan inverse of x dx. So again, you might think to yourself, why do we have to use integration by parts here? I only see one function in here, and that's tan inverse of x. Well, you can't take the antiderivative of an inverse trigonometry function without using some special integration method. So we're going to use integration by parts. Now we technically only have one function in here. So let's recall our favorite acronym, LIATE, and let's see what comes first. As I said before, if you just have one unrelated function, technically you can just do times 1, and then you have your second function right there. So 1 is an algebraic, tan inverse of x is an inverse trigonometry function. Which one comes first? inverse trig comes first before the a. So we're going to make u tan inverse of x, and then du is going to be its derivative, which if you don't know, is the derivative of what's inside. So it's just derivative of x is just 1, and then it's 1 plus whatever's inside squared, so x squared, and then dx. So for our second function, which is the 1, I should make this blue so you don't get confused. dv is just 1 dx, and then v is the antiderivative, which is x. Now again, we're going to use uv minus the integral of v du to set this all up. So when you do that, what you get is x times tan inverse of x minus the integral of x over 1 plus x squared. How did we get x over 1 plus x squared as our integral? If you recall, v was our x, and du was 1 over 1 plus x squared. And v du is what's in the integrand. So we essentially multiplied them together, which simplifies to just x over 1 plus x squared. Now we're going to have to use another integration method here. But thankfully, unlike the last time, we don't have to use integration by parts again. Because what we see here is we have our term in the denominator, x squared, is our variable, and then our term in the numerator is x, which is 1 power less. So what we can use is u-substitution. So u-substitution is pretty simple. We're going to have u as 1 plus x squared, and then du as the derivative, which is 2x dx. Now, our expression only has x dx, not 2x dx, so we're going to have to balance it out by dividing this by 2, and then we're going to have to divide by 2 outside the integral when we're all done. So what this ends up turning into when you use u-substitution is x times tan inverse of x minus half. That's where the division by 2 happens. Half of the integral of 1 over u du. And we switched our variable, so we also have to switch the dx to du, and then from here 1 over u is the same thing as u to the negative first power, which, if you know that integration rule, it's just ln of that variable. So x times tan inverse of x minus half of ln of absolute value of u plus c. And obviously we can't leave the u alone. If you don't remember what u was the denominator of that fraction in the integral, 1 plus x squared. So we're going to have to replace u with 1 plus x squared. So our answer is x times tan inverse of x minus half of ln of the absolute value of 1 plus x squared plus c. And even though this is our final answer, you may realize that this term, 1 plus x squared, will never be negative, because we have our variable being squared, so that can't ever be negative, and then it's added by 1, so it will actually never be below 1. 1 is the absolute minimum of that function. So because it's always positive, we actually don't need these absolute value bars, and we can simplify it even further to x times tan inverse of x minus half of ln parentheses 1 plus x squared plus c. These two expressions are equivalent, but if you're never sure on when you need the absolute value signs for the ln after integration, you should just keep them there. Moving on to our final example, and well, looks like we got a hard example. Anyway, we have sine of the natural log of x. So note the brackets and the parentheses, and note how this question is parsed. Let's recall once again Liate to figure out what we have to do. You might be tempted to say sine is the first unrelated function and ln of x is the second, but again, it's sine of ln of x inside of it. So this whole expression is actually just one whole term. So what we're going to have to do is we're going to have to again use times 1 so we can have our second unrelated function. So using that knowledge, let's set this up using Liate. So sine of ln of x is a trigonometry function because it is sine of a function. And then we have times 1, which is just an algebraic, so the algebraic comes first. So u is 1, du is actually just 0, and then dv is sine of ln of x dx. I apologize for how this looks. And then v, which is the antiderivative, and Well, we ran into an issue. Finding the antiderivative of this function is going to be very annoying, and it's probably not going to be worth it, which is why for this example specifically, I actually recommend you to just throw out the concept of liate. Let's just forget it exists. And we're actually going to make u sine of ln of x instead of 1. So we're going to have this as u, and we're going to have this as u. Okay, that d should not be there, but we're going to have this as u because finding the derivative of this function is undeniably going to be easier than finding the antiderivative. So du, we got to use the chain rule. So it's going to be cosine of ln of x, and then we have to multiply by the derivative of what's inside. Derivative of ln of x is 1 over x, so we just have all this over x, and then dv, as I said before, we're gonna make this one 1, and v is just x. And even though we didn't use liate for this one, we did it the other way around. This is gonna be much more simple for us to solve. After all, liate is usually designed to just set up u and v so that you solve it the easier way. So once we have all this, we're gonna set it all up using our equation, and what do we get? We get x times sine of ln of x minus the integral of cosine of ln of x dx. And we're gonna have to do another round of integration by parts. So once again, we're gonna throw out the concept of liate, and we're gonna make u the function cosine of ln of x. So let me write that down. And then du is going to be the derivative. So derivative of cosine is negative sine, and then we have what's inside ln of x, and then use the chain rule to multiply the derivative of what's inside. So derivative of ln of x is just 1 over x, so all that over x dx, and then dv is just going to be 1 dx, antiderivative v is x. So once again, use the equation uv minus the integral of v du, and what do we get? We get x sine of ln of x minus all of x cosine ln of x plus the integral of sine ln of x dx. And if you haven't realized already, let me just distribute that negative sign. You'll probably realize that we have to do integration by parts again. But not only that, this function sine of ln of x dx, this is exactly what we started off with. So if you keep using integration by parts here, you're actually going to go in an infinite loop. Kind of crazy, right? So what do we do from here? How do we escape this loop? Let's go on to our next page so we have more space. And you can notice that I minimized the font here because things are about to get crazy. So this is what we left off with. Keep in mind, this was our original integrand. We were asked to find sine of ln of x dx, and this is what we resulted. But you know what that means, right? That means that these two are actually equal to each other. This infinite loop is equal to the original integrand that we started with. So let's write that out. We have our equation, our whole expression, equal to the integral of sine of ln of x dx. So what do we do from here? Well, these two terms are the same. So what can we do? We can actually add this whole integrand. I'm not going to write it out, but we can add it to this side right here. And when we do that, we get x sine of ln of x minus x cosine of ln of x equals 2 times the integral of sine of ln of x dx. And then what you do from here is just divide by 2, so we're just left over with this amount. I apologize for how I wrote that, but our final answer turns out to be x sine of ln of x minus x cosine of ln of x all over 2 plus c, never forget the constant of integration, all that equals the integral of sine of ln of x dx. We successfully used not only calculus but algebra in order to solve this monstrous integral. And finding these infinite loops are very rare. You probably won't even encounter one anyway, but it's always good to be prepared. So I hope you guys enjoyed this 2-part tutorial, and I hope you guys have a nice day. See you guys later.